Now we should expect that this formula that we've calculated using a limit should give us the slope because we have used the slope formula to do this. The difference is all we've done is generalized for some point x, so we're now getting a formula that we can use x in. So if we take a look at example 2, this is really just a parabola. This is 3x plus 5. And comparing it to the parabola up here of x squared, really that's just a vertical expansion of 3. And if we take a look at a parabola, if we vertically expand it by 3, what's really happening to this graph? So we have a graph like that, and think of what's happening to the slope of that graph as I vertically expand it. In fact, if I vertically expand it by 3, it really should get a slope that is 3 times steeper than the original parabola at any point. So what we should expect then is when we generate the slope formula should calculate a slope that is 3 times bigger than the one that we calculated over here. Okay, because that was for x squared. We're now going to do this for 3x squared. So we should expect a 3 times bigger slope. So let's see what happens here. So if I take a look at my 3x squared plus 5, there's my graph. I've chosen some arbitrary point x. The y-coordinate of that's going to be 3x squared plus 5. And then I've chosen some point that is x plus h, or h units away from that point, and I've calculated the y-coordinate by plugging that x value into the equation. So I want to calculate the slope formula by using the slope ratio between those 2 points. I have my rise and run, so I'm going to do my limit. So my f prime equation for this graph is going to be equal to the limit as h approaches 0, and I'm going to get the rise between those 2 points. The rise is going to be 3x plus h squared plus 5 minus 3x squared plus 5. Okay, make sure I put brackets around there so I make sure I subtract the 5. Notice that those constants of plus 5 cancel out. Okay, and normally constants will cancel out because constants actually just shift the graph up and down. It doesn't actually affect the slope at any position of x. So let's do the expansion here. So we're going to go limit as h approaches 0. To simplify things, I'm not going to carry that plus 5 and minus 5 here. I'm just going to do the expansion of the quadratic. So I get x squared plus 2xh plus h squared minus 3x squared. I can kind of see that that 3 is going to multiply the x squared and we're going to cancel out. It seems very similar from the original one that we had here, but we have an extra multiplier of 3 out front. So we get the limit as h approaches 0, 3x squared plus 6xh plus 3h squared minus 3x squared. We can cancel out those 3x squareds. The h's are going to cancel. I'll do that in a separate step, but then we can see that the h's will cancel because now we have a factor of h. So I have h plus 3h. Okay, now those factors of h's will cancel out, so those cancel out here and here, and I can now evaluate my limit. This is going to be the limit as h approaches 0 of 6x plus 3h. Well, when I plug 0 into there, I'm just left with 6x. So what this tells me then is my f prime equation, which is the formula that calculates slope, is equal to 6x. And remember we talked about the vertical expansion. If we compare it to the original slope equation of 2x, I'm going to get a slope that's 3 times bigger for every point on x. And that makes sense because all this is going to do is stretch the graph up by 3. The plus 5 and the minus 9 in these cases, in the two examples, they don't really matter because all they're going to do is move the graph up and down. It's not going to affect the slope at any particular point x. So there it is. There is our slope formula for 3x squared plus 5. And we can test this by just plugging in different values of x, and we can actually see that those values, slope values, are quite reasonable.